One other important operator that we care about in this course is the divergence operator, the divergence of a vector. And the divergence of a vector gives us a number, a scalar. So it's an operator that converts a vector into a scalar. And the way it's defined, what you do here is that you do a surface integral over the closed surface surrounding a volume. So delta S is a closed surface surrounding a volume delta V, and then you try to see the flux coming out from that surface delta S, and then you divide it by the volume, and then try to make this volume as small as possible. So in general, so what I do here, I draw a very small surface, closed surface, here as shown here, and then we try to determine the flux of the field, the surface integral coming out from that surface, and then we divide by the volume delta V or d delta V, whatever inside that, surrounded by that surface. And of course we talked before about differential elements. We talked about differential volumetric elements in cylindrical, spherical, and Cartesian coordinates, and there are lengthy proofs that shows you how to get the expression of the divergence in these coordinates by using the different elements we talked about. In Cartesian coordinates, the element is a very simple one. It's parallel to the xy axis. In cylindrical coordinates, we have seen before that the element looks something like this in the rho and theta and rho and phi and z dimensions and so on. And there is also similar one in the spherical coordinates. So if you do the integral over this differential surface and using Taylor expansion and then you divide by the volume, you will be able to obtain the expression for the divergence in Cartesian, cylindrical, and spherical coordinates. And you don't have to worry about these expressions, you just have to include them in your cheat sheets, but you should understand how to use them. And keep in mind that the divergence converts a vector to a scalar, and it varies from one point to another. It may vary from one point to another, and divergence measures the existence of a source at that point, as I will show you now. Now, as I mentioned, the divergence measures whether there is a source or not at that point. So it's really it acts more like a probe in electrical engineering. For example, here I have a point B. Maybe take a look at this figure here. I have a point B, and the field lines are all starting at point B. They are diverging from point B. So if I do a closed surface integral over this cylindrical shaped tiny cylinder, the integral here of the field, I will call it here d dot ds, will likely be a positive number. Why it's a positive number? Because all the field lines, they make an angle less than 90 degrees with the normal to the surface. So f dot ds will give you a positive answer in all three parts of the cylinder: the side wall, the top wall, and the bottom wall. So here we can say that there is a positive charge here, and this is actually what we have in electrical engineering. Later you will know that if you have a positive charge at one point, that the field lines all diverges from that point. They start at this point in the static case. The second figure, figure B, shows you a charge or a point where field lines are converging to that point. Of course, if you try to calculate the integral here of d dot ds, you will get a negative answer. Why? Because the field is flowing toward the surface while the normal to the surface is pointing in the opposite direction. So d dot ds will always give you a negative answer. So if you collect all the contributions coming from the three surfaces, you will end up with a negative answer here. This is telling you that there is a sink. That the field lines are converging, they are not diverging from that point. And this is what happens in our electromagnetics when there is a negative charge q minus q at one point. Electric field lines will converge, will end on that negative charge. The third one here is the case. The figure C shows the case of a divergenceless field. The field lines are not starting nor ending on P. They will enter, these flux lines will enter part of the surface, the closed surface, and will leave the other part. So if you do the total integral of d dot ds, you will get 0 because the net flux is 0. So if you take the limit as you make this probe extreme, or make this cylinder very tiny, very small, and you divide by the volume, this will be a measure of how the field is diverging, converging, or it's neither diverging or converging, it's zero divergence at a point. and we can do that at every point in space. So this divergence operation or operator is really equivalent to having a probe at a point measuring whether there is a source or not. When the divergence is positive, this means there are positive charges, as in electrical engineering. When the divergence is negative, this means the field lines are converging and there are negative charges. The divergence through two examples. So I would like you to calculate the divergence first in cylindrical coordinates of the function rho a rho plus z sine phi a phi plus 2 ez, and the second one in spherical coordinates of 2 a rho plus r cosine phi a theta plus r a phi. Of course, I don't memorize the expression for the divergence. I just know how to use them, and you should just know how to use them. And the derivation of these expressions is pretty lengthy. I would like you to read it, but don't memorize it. Just through understanding to understand where did this come from. Starting for the cylindrical coordinates, you will see that this is the expression for the divergence. You take the rho component of the vector, multiply it first by rho, and then you differentiate this product relative to rho, and then you divide by rho. For the phi component, you differentiate relative to phi, and then you divide by rho. For the z component, you differentiate relative to z. So for the f rho that we have has only rho in it. So you multiply rho by rho, you get rho squared as shown here. So the derivative of rho squared with relative to rho will give you 2 rho. You divide by rho, you get 2. For the other one here, which is the phi component, you do exactly the same thing. You differentiate the sine phi. Derivative of sine phi related to phi here will give you cosine phi, and the z, of course, is not z comes out from the differentiation because it's not a function of phi, and you divide by rho as you see here. So the answer that you get is z over rho cosine phi. So then the divergence here at any point in space is equal to 2 plus z over rho cosine phi. Repeat exactly the same things here for spherical coordinates. So the expression for spherical coordinates is a little bit more complicated. So you could see here we have first you multiply the r component of the vector by r squared, and then you differentiate this product here, differentiate it relative to r, and then you divide by r squared. The derivation of this you can find in many mathematical books. For the theta component, you multiply the theta component by theta, and then the product you differentiate it relative to theta, and then you divide by r sine theta. For the phi component, you simply differentiate relative to phi, and then you divide by r sine theta. In our case here, fr was equal to 2, so it's a constant. So the derivative of 2r squared will give you the term that we have here. You differentiate this one relative to r, and then you end up with I believe here, let's see, this is here 2r squared. You divide by r squared, so we get this term here. For the theta component, we had cosine theta. When it was r cosine theta. So when you differentiate, you multiply it by sine theta. So this will give you 1/2 sine double the angle. So what I did here, I made a fast step. I multiplied cosine theta by sine theta, and I wrote this as 1/2 cosine double the angle. And when you differentiate 1/2 sine double the angle, and when you differentiate sine double the angle, you get cosine 2 theta as shown here. And then of course you had r in the expression, it will cancel out with this r. You end up with only sine theta in the denominator. So this is how this divergence is calculated in the spherical case. One of the most important theorems in electromagnetics that you see very often in this course is divergence theorem. And the great thing about the divergence theorem is that it converts a closed surface integral, which may be difficult to do and has many parts, it's done over many subsurfaces, into one volume integral over the volume enclosed by that surface. And I thought I should show you here a very simple proof of this theorem, if I may say. And here what's happening, if you take a look at the figure to the left, you see that we divide the volume of interest into volumetric elements, so differential elements. And they cover the whole volume regardless of its shape. And then from the definition of the divergence over every one of these tiny elements is by definition equal to the integral over the surface of this element. So the integral over of f dot ds over delta si, the surface of the I element, divided by the volume, so divided by delta vi. So here if we just remove the limit and assume that the element is small enough, then the integral over the surface will give us the divergence multiplied by the volume of that infinitesimal element. And then what's happening next is that we sum the flux contribution coming from all the elements. So we do a summation from 1 over to n. We assume here that we have n capital volumetric elements. And we do the same on the right hand side as well. One thing to notice, if you take a look at two neighboring elements as shown here, the i's and the I plus 1, they share one surface. They share this internal surface, and the unit normal for the first one is pointing in the outward direction. The unit normal for the first one is pointing for the output in the outer direction, and these two directions are opposite to one another. So the contributions coming from the surface integrals from these internal surfaces will cancel out, and you end up only with the integral over the external surface of the whole volume. So all internal contributions will cancel out because they are shared between two elements. Only the external surface elements, like the one shown here, I'm trying to highlight here, will contribute an external surface in the outer surface. So if you do that, you will notice that this will actually take the limit as n goes to infinity. This becomes an outer surface integral over the surface enclosing the total volume, and this will the right hand side, the summation here becomes a volume integral because you are summing over the whole volume. So what is this telling you? You can, of course, if you have a closed surface enclosing a volume, either you calculate the flux through a closed surface integral of f dot ds, or you can calculate it by first calculating the divergence of f, which is a scalar, and then integrating it over the volume enclosed. And this is the brilliance of this theorem. You can either do a surface integral, which you can have many sub-surfaces to be integrated over, or just one volume integral of a way simpler function. Remember that the divergence requires you to do a differentiation of the function, and it gives you a scalar thing. So here you are doing actually a scalar integral, while here you are doing a vector contributions. To illustrate the divergence theorem, we'll consider this example, which is done here in cylindrical coordinates. So we have a vector d. It has two components, a rho and az, as shown here. And we would like to calculate first the surface integral over the closed surface, and then the divergence of the volume over the volume enclosed, and this is over the region defined by rho between 2 and 5, z between -1 and 1, and phi between 0 and 2 pi. So it's a cylindrical shell surrounded by the cylinders, rho equal to 2 and rho is equal to 5, and z between -1 and 1. So for the cylindrical shell, and maybe I can try to draw for you a figure here. This is how things look like. So this is how this shell looks like here, and of course it goes from -1 to 1, and this is the inner part of it, of the shell. It doesn't show, of course, it's hidden. So you can see here that we have to integrate over four surfaces. There is the top part. There is the bottom part, which is this one here, and then there is the outer part, and there is the inner part. We did a similar example to that in the lecture. And you have to do here 4 surface integrals. Each one of them will have its own surface element. For the outer integral, the surface element as shown is rho d phi dz. For the top surface, the surface element that you will need here is rho d phi d rho. For the bottom one is the same. For the inner one, it is the same one like the outer one, but it's pointing in the minus rho, not in the rho direction. So we have 4 integrals to do, which makes this example a little bit interesting. So let's start doing these 4 integrals. As I explained, this integral has four parts. Integral over the top part, this will give you the flux from the top surface. Integral over the bottom surface. Integral over the outer part, which is a four cylindrical surface, and integral over the inner surface part, which is also a cylinder but with minus arrow pointing inward. So let's do the top one. The top one, you will have to integrate. The unit surface over there is rho d phi. It's pointing in the z direction, so only the z component of the vector will remain. So you have here rho cosine squared phi. So integrate rho cosine squared phi az dot rho d phi az. Of course, to cover the whole top base, a will change from 2 to 5, phi from 0 to 2 pi. The integral of rho squared, here we have rho squared, rho multiplied by rho. It will give you rho cubed over 3. You put 2 to 5, 5 squared, 125, 2 squared. So you do this subtraction here. So 125. If you simplify things, you will notice you get 125 minus 8, you get 117. The cosine squared that will remain inside cosine squared phi, I will express it as 1/2 1 plus cosine 2 phi as shown here. So we express it this way. The integral of cosine 2 phi will give you sine 2 phi, but because you're integrating over from 0 to 2 pi, you get 0. The integral of this one will give you phi. Phi from 0 to 2 pi will give you 2 pi. You divide by 2, you get pi. Then the answer becomes 117 pi for the inner, for the top base, for the top disk here, the top surface. The bottom surface is not that difficult to show that the direction of the unit normal is really minus az, and it's exactly the same integral except for this negative sign. So I will leave it for you as an exercise to show that if psi b, the flux from the lower base, is equal to minus 117 pi. Now what remains to do the outer and the inner integrals? So for the outer cylinder, we know that the unit area, as we explained before in the lecture, so this one here is rho d phi dz. Rho d phi dz, that's pointing in the rho direction, and rho here is a constant, rho is equal to 5. So we are integrating here the rho component, which is 2 rho z squared. You multiply it by rho d phi dz, and you integrate over z from minus 1 to 1, and you integrate phi from 0 up to 2 pi, and you replace every rho by 5, because this is done for the outer cylindrical surface. So this rho squared will give you 50. This rho squared will give you 50. You multiply by 2, you get rho squared will give you 25. You multiply by 2, you get 50 here. Now we have to integrate over z. We have z squared. The integral of z will give you z cubed over 3. You put upper limit minus lower limit, so this will give you 2 over 3. And then the integral of the phi d phi will give you phi. So it will multiply again by 2 pi. If you put all this together, you get an answer of 200 pi over 3. Now the integral for the inner cylinder will be exactly the same, except that for the unit outward in the minus a rho, and the rho squared that you have will not be 25, it will be 4. So I can save lots of time by saying that from my experience, the value of the flux from the inner surface is equal to the outer flux epsilon naught here, multiplying by minus 4 over 25. And the reason is simple. Negative sign is that the unit normal is in minus a rho, not the a rho. And because inside the integral there is rho squared, which is constant, rho squared for the outer cylinder is 25, and rho squared for the inner cylinder is 4. Explained, we simply say that if psi in is minus 4 over 25 if psi out. So this will be the value of psi in after you multiply by 4 over 25. 200 over 25 will give you 8. You multiply by 4, so you get minus 32 pi over 3. So now the total flux is the sum of all fluxes. The top and the bottom one will cancel each other out. You are left only with the outer flux minus the inner flux. So this gives you 168 pi over 3. This, you could see this one took 4 integrals in order to calculate the flux coming out from that surface. But divergence theorem tells us, you know what, we could have saved lots of time by getting the divergence of D, the divergence of the vector, and then integrating it over the volume, and we just have one integral. So the divergence here in this case, because the function is a function of rho, it has d rho and dz components. Divergence cylindrical coordinates will have this form here: 1 over rho partial rho d rho plus partial dz partial z. So the rho component first multiplied by rho as shown here, and then you differentiate it relative to rho, and then you divide by rho after that. And the z component you differentiate it relative to z. So if you do that, you will see that the second term will give you 0. The derivative of rho squared will give you 2 rho here. Z squared becomes a constant. So you cancel out this one here, and you end up 2 by 2z squared. You end up by 4z squared. So you see, even the term is very simple. The divergence is 4z squared. So our target now is to integrate over this whole volume 4z squared. Of course, in order to cover the whole volume, we use a volume element in cylindrical coordinates, which is rho d phi dz. And to cover the whole volume between the two cylinders, the two cylinders have something like this, look something like this. So rho will have to change from 2 to 5, z will have to go from -1 to 1 to cover the whole surface, and phi from 0 to 2 pi. So this is why we get all these bounds here. The integral, of course, we can simplify things here. The integral of rho d rho will give you rho squared over 2. So you put the upper limit 25 minus the lower limit 4. So this is how we end up with 21 here. I try to make the steps a little bit faster way so that you get used to these calculations. The integral of z squared will give you z cubed. So z cubed over 3, so this is why you get to this 3 here. You put upper limit will give you 1, lower limit -1, so it will give you 2. So 2 multiplying 2, you get 4 here. Now the integral of d phi will give us phi. You put upper limit minus lower limit, so this will give you 2 pi here. If you simplify all this, 3 will cancel with 21, so you get 7. 7 by 4, 28 by 2, so this will give you 56 pi. And 56 pi, by the way, is equivalent to 168 pi over 3. When I got this initial result I did not simplified. So this is equivalent to the total flux. So this example shows you that you can, in making these calculations, you can go either way. Either do a number of surface integrals, which will take a long time, or simply calculate the divergence of D and then integrate over the volume enclosed by that surface, and you'll get exactly the same answer. So the divergence theorem is very important, and as we will see later, it will help us in driving Maxwell's equations in the differential form. They are very important for the derivation of Maxwell's equation in the differential form. Second example on divergence theorem, I thought of giving you one more example in spherical coordinates. So we'd like to consider this vector D, which has only an r component, spherical coordinates, is equal to 3r squared dr, and we'd like to verify the divergence theorem by over the region enclosed by the spherical shells r equal to 1 and r equal to 2. So what we have here, we have an inner sphere, we have an outer sphere. So we're talking about a spherical shell. And the spherical shell has two surfaces: the outer spherical surface with unit vector AR pointing outward, and the inner spherical surface with minus AR pointing inward. This one, the inner one has a radius of 1, the outer one has a radius of 2. So if we were to apply it to get the total flux coming out from this surface, what we have to do, we have to do two surface integrals, one over the outer sphere, this one, and one over the inner sphere. Or we can get the divergence of this vector and integrate it over the spherical shell, the volume of the spherical shell between both surfaces. They should both give exactly the same answer. First, we start by calculating the flux. So we do an integral over the inner sphere, a spherical surface, and another surface integral over the surface of the outer sphere. For the inner one, the unit vector, remember the unit area is minus r squared sine theta d theta d phi. These are spherical surfaces, so r does not change, only theta and phi will change. And remember, for the inner spherical surface, the unit area is pointing inward, so this is why we have this negative sign here. So you multiply 3r squared ar dot minus r squared sine theta d theta d phi ar. You get ar dot ar will give you 1. And in order to cover the complete surface of the sphere, theta will be integrated from 0 to pi, phi will be integrated from 0 up to 2 pi. You do exactly the same thing for the outer sphere. For the outer sphere, again, it's 3r squared, but the unit area is r squared sine theta d theta d phi, and it's pointing outward in the positive ar direction, and exactly the same bounds. So remember, in the first integral, this one here, every r will be replaced by 1. In the second integral, which is for the outer one, every r will be replaced by 2. So this will give us here, you get minus 1, and this one here will give us, so this one will give you these integrals here. So this is 40, you get from this one 3 multiplied by 16, so you get 48, while for this one here you get 3 multiplying 1, so, with a negative sign, so you get minus 3. So 48 minus 3, you get 45 here. This is how this 45 we obtained it, okay? And what remained is to integrate sine theta from 0 to pi, and you integrate d phi from 0 up to 2 pi. Integral of sine theta will give you minus cosine theta from 0 up to pi, will give us here 2, because it's upper limit minus lower limit, so you get 2. And then the integral of d phi will give you phi, upper limit minus lower limit will give you 2 pi. So the whole result of this one will give you 4 pi. 4 pi you multiply by 145, you end up getting 180 pi as a final answer. Answer, as I explained earlier, is 180 pi. Now, doing the other way around implies that we get the divergence of d, and then which will be a scalar, and then we integrate over the volume. Divergence of d in spherical coordinates means, because we have only the r component, you multiply this component by r squared, you differentiate it relative to r, and then you divide by r squared. So if we do that, dr is equal to 3r squared, you multiply by another r squared, you get 3r to the power 4. If you differentiate it, you get 12r to the power 3. So if you divide here by r squared, you get 12r. I had a typo here in the solution which I fixed, so you can see the answer. The answer should be 12r and not 12r squared as it was typed, but everything else is fine. So my answer for the divergence 12r. So now I'll take this divergence and then I will integrate it on this spherical shell. So in order to span the whole spherical shell, we'll integrate the volumetric element we know in spherical coordinates, r squared sine theta, dr d theta d phi. We'll integrate it, r will go from 1 up to 2, theta from 0 up to pi, and phi from 0 up to 2 pi. So by doing that, we cover the whole surface. So now we would like to integrate 12r cubed relative to r. So this will give us 12r cubed. So it will give us r to the power 4 divided by 4. So this will give you 3r to the power 4. We substitute the upper limit minus the lower limit. So the upper limit will give us 2 to the power 4 will give us 16, minus 1, so it gives us 15. You multiply this by 3, you end up getting 45 here. And then we integrate sine theta, will give us minus cosine theta. Minus cosine theta from 0 to pi will give us 2. So we end up with 2 as well. The integral of d phi from 0 to pi, 0 to 2 pi will give us phi. So you put upper limit minus 1, you get another 2 pi. So the total answer you get from this integral here, you'll get 4 pi. You multiply by 45, so you get 180, which is the same integral we got by doing 2 surface integrals here in this case. One on the outer spherical surface, the other one is the inner spherical surface. So you can see that the divergence theorem simplifies things a lot. And later you will realize the meaning of this, integrals, the meaning of the total flux, and the meaning of the volume integral when we start to talk about charges and the electric charge density, the electric flux density, and the electric field. So this will be coming very soon next week.